important question. So we talked about correlation, regression, some of the assumptions. We'll get into that a little bit more. Remember that if we're technically talking about a correlation, we're assuming random variable X and random variable Y. Evelyn, can you remind me what we're talking about if we're talking about a random variable?
That you just like select it out of the hat.
Yeah, it's just we get what we get, right? If I go through and run a survey and I want to look at sort of modern racism, right? I'm just gonna, that's a random sample. I'm just gonna get values. I'm not gonna get all possible values, but I'm gonna get some selection of things versus a fixed variable. Hey, how do we define a fixed variable or no fixed variable?
You'd have a specific value in mind that you wanted to use.
Right, we're sampling individual values. So if I say, if I want to have a good, if I've collected modern racism as a fixed variable, I'm saying I have 20 people at this level, 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 right? I have representation of all possible variables. That's going to be a fixed variable, right? And so technically this, with a regression model, the underlying assumption of classic regression is that our predictors are fixed variables, right? Now this isn't what actually happened when we actually run regressions, so we have to make some modifications and additional screening to make sure that the violation of this primary assumption isn't going to go through and impact our tests and our inferences. And so same thing with our linear regression models. With our correlations, we're expecting error in our measurements of X and our measurements of Y. But for regression, we'll talk about this down the road, we're expecting only error in the variance, or error variance, or sampling error in the collection of our outcome. We're assuming that our predictors are measured without error. Once again, we violate this, right? And so we'll talk about down the road what the consequences are, how we get around some of that stuff, or just accept it. Talked about properties of correlation coefficients, and then jumped into guess the correlation game. How are people doing? What's anybody high score? Guess, you guys haven't been playing guess the correlation? I'm serious. Big prize, big exciting prize for high score on guess the correlation by the end of it. You're going to be sad if you miss out. So all your extra time not spent in this class should be spent on this game. All right. So going to go back through, do some basic review of concepts that we covered in depth last semester. First thing, variability. Remember, if we're talking about variability in general term, talking about the extent to which scores in a distribution spread out or clustered together. Okay. If everybody's the same, no variability. If there are large differences in individual scores, we're saying that there's a lot of variability. You want to be able to think about variability and have a good conceptual idea of what this looks like in your head as we're moving forward through some of these more complicated analyses. Thinking about variability in terms of distance, right? If I have a distribution of scores, here's the center, here's my here's my measure of central tendency. My variability measure tells me how much are things spread out or clustered together. Again, thinking about this as our different measures, we can think about this as the expected distance between any two individual scores, right? If I take Evelina's bin of random scores and I pull one out and pull another one out, if I have a measure of variability, that should tell me on average how much distance I should expect between those two randomly selected scores, or any individual score that I would pull out of there in the mean, right? Tells us how well any individual score within our sample is going to be representative of the entire distribution. So use this when I was trying to explain similar concepts to my Psych 1000 students, right? If I were to assess undergraduates' age and undergraduates' physical weight, which one of those variables is going to have more variability to it? Weight, yeah, why is that?
It's going to be more distance.
It's going to be all over the place, right? Age, not that we're not going to have variability, but most undergraduates are going to be at 18 to 20, 21-ish range, right? But I think for thinking about conceptually what we're talking about in terms of variance, right? If we start to apply those two examples to some of these conceptual definitions, right? If I'm thinking about variability as an indicator of how well any randomly selected individual, how representative, how well any randomly selected score is going to represent the larger distribution. If I select a random undergraduate's age, I'm probably a lot more confident that that person is going to be representative of undergraduates more generally than if I were to randomly select anybody's given weight, right? If you give me a bin of weights and I pull it out and I say, oh, this undergraduate weighs 180 pounds, how representative that is undergraduates in general? I don't know, probably not great, right? But if I pull out an age and I say it says 19, how representative that is undergraduates' age, I say pretty well, because I know that's a pretty tight distribution, right? Same thing if we're thinking about variability in terms of distance between any randomly selected score in the mean or any two randomly selected scores. I would expect two randomly selected ages from that back to be much, much more similar than two randomly selected scores of someone's undergraduate's weight in pounds, right? We get wide variability there, right? So this starts to become important in thinking about variability is going to be the basis for pretty much everything we do from here on out. It has been still before, but one, you get a strong sense for sort of conceptually what's going on when we talk about variability in scores and how that starts to become important, how we can start thinking about this carefully. I think this is, again, and I mentioned this last semester, in our statistics, we tend to focus on measures of central tendency in terms of interpretation, which is fine, right? So this group scores on average higher than that group, cool. That's important information to know, but I think we often overlook variability in our scores, right? Because we say, well, so let's say Kate's running a study and has these folks engage in one task and these folks engage in another task. I see on average this group is higher than this group, but I have way more variability in scores in this group as opposed to that group, right? That tells us something about what's going on. Here, whatever we're doing in this group in terms of our manipulation, we're getting the same scores over and over and over again. We're getting a pretty tight cluster. Over here, we have some higher, but some a lot lower. A lot of variability. We can start to think about that in terms of something that's meaningful for understanding psychological phenomena. So, we often just sort of look at standard deviation, skip over it, and things like that. But would encourage you to start thinking about that more carefully and what that means in terms of outcomes. Again, for clinical folks, right? If I have a treatment, do I want more variability or less variability in treatment response to something? Less variability, right? That tells me something. That says, hey, this is working really good. Everybody who goes through here is getting consistently better about the same level, right? Instead, what we typically focus on is how do we see a mean change? Do we see people evidencing mean reduction? Well, maybe, and that's part of the story, but also if I have huge variability in how people respond, some people get a little bit better, some people get a lot better, some people might get a little worse, some people might get a lot worse. That's variability I need to be thinking about in terms of making a reasonable interpretation about what's happening with my stuff. So all this is review, but people kind of clear on variability stuff? All right, variance, a very specific type of variability. Thinking about this as your second population moment, your mean being your first population moment, variance being the average squared distance from the mean, okay? Variance is going to be huge. We're going to be doing a lot of work with variance this semester. If we go through and we take our variance estimate and we take the square root of that, we get our standard deviation. And again, one, you have a good conceptual idea of this, thinking about your standard deviation loosely as the average distance of any given score from the mean, right? So on average, if I were to pick any score, random score from this distribution, on average, how far is that going to be from the mean? Why do I say loosely estimated or loosely interpreted as the average distance of any score from the mean? Yeah, so I'm saying loosely interpreted is the average distance of any score from the mean. Why loosely? Remember? If we're talking about the population, it is the average distance of any score from the mean. If we're talking about samples, it's roughly the average distance. Why roughly?
Well, because it's not the exact same as the population.
Yeah, yeah. And so what do we do to that sample statistic that changes it a little bit?
I mean, there's error within that, so.
There's error. What do we do computationally when we're calculating sample variance that's different than calculating population variance?
Subtract 1.
Yeah, right. So it's not exactly the average. Now, if I've got 300 people, it's functionally the average, right? If I've got 10 people, you know, right? So when we're going through and we're calculating this, conceptually, you can think about standard deviation as the average score, the average of any score from the average distance of any score from the mean, or the average distance between any two randomly selected scores. It's not technically the average distance because we're dividing by n minus 1 instead of n, but it's a nice way to start sort of thinking about this, right? And so again, yeah.
Can I just ask a question? So I'm noticing that some of the slides that you have up on the board don't line up with the ones that we have. Is that intentional?
Let me see what you've got.
It's missing the second population.
Oh, okay. Yeah, it's not. It won't be a big deal.
Okay.
But I'll go through and try to make sure that we've got sort of other stuff on there. So yeah, just write down a
Okay.
second. If there's something that's not there that seems big, let me know and I'll make sure I go through and change it. Okay. All right. So calculating variance, right? As we're going through, and I think this is a nice way because it kind of helps you visualize what's actually going on with the calculation of our variance estimates. Let's say we have a set of 5 scores. Okay, these are our x values. First thing we want to do is we want to calculate a deviation score for each value, right? Deviation score is just how far any one of these individual scores is from the mean value. Okay, so we first calculate our deviation scores. Okay, and this is just, if I say, oh, calculating deviation scores, this is just how far any individual score falls from the mean. Again, this is something that's going to come up again and again and again and again, so just want you to be familiar with this. So step 1, calculate our deviation score, and then what we're going to do is we're going to take the square of each one of those deviation scores. John, why are we ultimately going to square those deviation scores?
So it gets rid of negative values.
What's that?
If there's any negative values, it gets the positive.
Yeah, so why don't I want negative values? Negative values are nice because they tell me that it's above or below the mean. Why do I want to get rid of those?
Because then it sums to 0.
Yeah, if I try and add those up, by definition, the sum of my deviation scores will equal 0. And so what I need to do, if I go through and I sum that, if I square all of those, it gives me a metric that's not as interpretable, but I can start to work with and do stuff with that, right? And as we start to get into things like regression, things along those lines, our OLS regression is based on squared deviations, but there are different approaches, absolute deviations and things along those lines that you can use to derive some coefficients and things along those lines. But if you want to know what those are, it's nice to kind of understand how we're going to go through and just do standard stuff. So we calculate our deviation scores, and then we go through and we sum those square deviation scores, and we get our sum of squares. Okay, sum of squares is literally the sum of your square deviation scores. Sum of squares, again, is one of these metrics of variability that isn't super interpretable. Like, I can't just look at a sum of squares and tell you whether or not that's big or large or small. The sum of squares is integral. It's a huge piece of the calculation of a great number of our different statistical procedures. And so when you see sum of squares, sometimes people get freaked out and their eyes glaze over. They'll be like, I don't know what sum of squares are. It's just literally the sum of the square deviation scores, and it's just a general measure of variability, right? I can't look at it and tell you if it means a lot of variability or not a lot of variability. It's just a measure of variability in this set. But what we can do to make this a little bit more useful, sort of working towards something that's more interpretable, is we can take that sum of squares and divide by our degrees of freedom. This is going to be the number of scores in the sample minus 1. Okay? This is going to give us our variance estimate. We can start to use variance. Variance, again, is just a reformulation of that variance estimate, adjusted for the fact that we're drawing from a sample instead of using the whole population. Okay? Remember, the idea behind this adjustment is that our samples, if we were to just take our sum of squares and divide it by the number of observations, it would always systematically, from a mathematical standpoint, underestimate the population variability over time, right? Because if this is the population variability, I've got like 1 or 2 people here out at the end, the likelihood of me capturing those systematically is going to be fairly low. Most of my sample is going to come from the middle, and so what ends up happening is we go through and make this small adjustment to get our sample variance as an unbiased estimator of the population parameter. Okay? So as our samples get larger and larger and larger, what impact does this have on my overall variance estimate? Relative to just dividing by the number of observations.
Sorry, could you repeat it?
Yeah, so as my samples start to get larger and larger and larger, what's the functional impact on my variance estimate if I divide by n minus 1 versus n?
It gets larger, or it gets smaller.
Yeah, right. So if I've got a sample of 500, my variance estimate that I calculate using the sample statistic formula versus the population formula is going to be next to nothing, right?
Yeah.
But for smaller samples, which oftentimes in psychological science is what we're working with, right? Haley, you're running an experiment in Raina's lab, right? You don't have the time or the resources to run 500 people. You can get 20 people in a cell, right? Now all of a sudden this starts to help make that estimate unbiased, right? So we go through and calculate our sample variance here, and then we take the square root of our variance to calculate my standard deviation here, okay? And again, standard deviation, now we're back down to something that is more interpretable, right? Because we've gotten this back basically to units of our original measurement, and so I can take a look at that standard deviation and have sort of more interpretive value that I can say, on average, this is the expected difference between any 2 scores. Randomly selected scores are the average distance from any randomly selected score from the mean value. So I can expect sort of on average, 2/3 of my sample to probably, if it's following a normal distribution, to fall between standard deviation above, standard deviation below. Lots of different stuff that we could start to do when we're back here. But standard deviation, variance, and sum of squares, these are all measures of variability of our data, just kind of expressed in different units. Questions on this? Okay, you look like you have a question.
No, I'm
No.
just trying to make sure my note was right, but I think it is.
Okay, cool. All right. Comfortable with this? This should all be refreshers. See how easy that is to learn like the second or third time than the first time when it's all confusing? Right? You're gaining statistical knowledge. Computational formula. So this is kind of conceptually how we would go through and work it, but this would be a lot to do. Computationally, you can calculate your sum of squares as the sum of your squared x values minus the sum of your x squareds. I think that should be squared, not 2. Am I right on that? Angela, can you shoot me an email to go back through and try and fix that? Because otherwise I'm giving you formulas that are wrong. If I multiplied everything by 2 and I'm getting the wrong answer, that should be a squared thing there. Okay. But again, just computational formula, so you can go back and forth there mathematically. All right, new stuff, covariance. Okay. Covariance is going to represents the extent to which 2 variables vary together, right? And so if we're calculating covariance, covariance of x and y is going to be equal to the sum of my x value for individual score, individual x, minus the mean of x, times individual y, times the mean of y, over n minus 1. And so, if we're looking at a set of data, again, this is the scores for survivors of motor vehicle trauma. Okay, this red line here represents the mean of our PTSD scores. This vertical blue line is the mean of our depression scores. Right? And what we can do is we can start to calculate the covariance of my depression scores and my PTSD scores. And this measure of covariance is going to give me a sense, start to give me a sense and start to allow me to calculate the extent to which these two variables vary with one another. Okay, so if I'm looking at my formula, and again, I want to emphasize this, a lot of times we sort of want to look over our formulas and sort of not pay much attention to that because I have a computer program that'll go through and do this for me. But this mathematical formula will really help you understand what's actually going on in the calculation of these statistics, which really helps with problem solving down the road. When something goes south, you don't know why, you're getting answers that don't make any sense. So looking in it and sort of saying, what's this, should this actually be doing, can be a helpful way to assess difficulties. So if I have two variables, and for individuals, if large X values are paired with large Y values, the sum of the products of my deviation scores are going to end up being large and positive, right? So if I, on average, large BDI scores, right? So large depression scores, let's say this person right here. On average, I have the large depression scores are associated with large PTSD scores. What's going to end up happening is, all right, if I have this score right here, and this is my X, what's the value of this score minus the, or excuse me, this score minus the mean of depression here? It's going to be a large positive number, right? Correspondingly, if I take that same person and take their PTSD score and subtract it from the mean of the entire sample, what's this value going to be? Large and positive, right? And if I take a large and positive number, multiply the large and positive number, and if on average this is what's going on, my covariance is going to be large and positive, right? Same thing, similar for small X scores. Hey, if I'm looking at this person right down here, right, they've got a depression score that's way below the mean, but correspondingly, their PTSD score is also far below the mean. I'm going to look at a large negative score. What happens when I multiply two large negative scores?
Large positive.
You get a large positive score, right? So my covariance here is going to be large and positive. By contrast, if I happen to have a situation not like this, but I have large X values paired with small Y values, right? If on average, my big X's are paired with small Y's, right? Laura, what's this first number going to be?
Large X's?
Yeah.
That means it's going to be large and positive.
Large and positive, but if my large X's are paired with small Y's, what's that one going to be? It's going to be negative, right? Large and negative, right? And so if I go through and I multiply positive and negative together, on average I'm going to get a negative covariance, right? This is going to tell me that I have an inverse relation. As X is large, Y's tend to be small. When X's are small, Y's tend to be large, and what we end up getting is a negative covariance estimate, suggesting that things are working in the opposite direction. I have an inverse relation, right? But in situations where X's are unrelated to scores on Y, right? John, if I'm looking at this, sometimes X minus X squared is going to be large and positive. Sometimes it's going to be negative. If there's no relation between X and Y, the corresponding Y will sometimes be large and sometimes be negative. Sometimes it will be above, sometimes it will be below. What's going to happen to the numerator of this equation in that situation?
Sometimes big, sometimes small.
Yeah.
All over the place.
It's going to cancel out, right? We're going to end up, on average, getting something in the numerator of this that's going to be close to zero. Everything's going to cancel each other out, and what we're going to end up with is a covariance that's somewhere near zero, right? Knowing something about X tells me little to nothing about what's going on with Y, and so my covariance is going to be, again, something close to a null value. So people kind of see how this specific formula is starting to capture the extent to which these two variables are related to one another, or the extent to which they vary together. Okay. So again, just like with our sum of squares, you have a computational formula for covariance that's easier to calculate than sort of all of this, right? Because you would need a spreadsheet, create sort of deviation scores and multiply them and so on and so forth. If we take the sum of our x and the sum of the product of our x and y scores minus the sum of x times the sum of y over n all over n minus 1, that'll mathematical equivalent. That'll also get you a covariance estimate there. Okay. So this takes us to our Pearson correlation. Call this our Pearson product moment correlation. We know that absolute value of our covariance, right? This covariance coefficient that we just calculated is going to be a function of the standard deviations of x and the standard deviation of y. Okay. Covariance by itself doesn't have a lot of interpretive value. I say, hey, here's a covariance estimate. Tell me whether or not it means that, how strong the relation is between these variables. You're not going to be able to tell me. It's not a meaningful thing. But what we can do is if we take that covariance and we divide it by the standard deviation of x and y, what it does is it standardizes that covariance estimate so that we'll end up with a coefficient of value that's going to range from -1 to 1, right? So thinking about covariance as the equivalent of variance when we're talking about variability estimates. Your correlation coefficient is kind of like your standard deviation. We're taking something that's just kind of a general measure of covariation, and we reduced it down, standardized it into something that's more interpretable that we can take a look at regardless of what our actual metrics are and say, oh yeah, this reflects a strong correlation or a weak correlation, so on and so forth. Okay. So our Pearson product moment correlation is going to be calculated as the covariance of x and y over the product of the standard deviation of x and the standard deviation of y. Okay, so I can take a covariance estimate. You know, I know the standard deviation of x, standard deviation of y. I can calculate a correlation quickly and easily with that. Okay. One thing, and so you all, I'm positive, are familiar with generally how we interpret correlations, and you use them all the time and see them, things along those lines. One thing to remember, though, is that Pearson correlation R, this is not going to be an unbiased estimate of population parameter. Okay. Someone remind me if I'm talking about whether or not a statistic is biased. What does that mean? Does anybody remember? I've got a biased statistic. I'm saying that this value is going to systematically overestimate or underestimate the actual population parameter, right? It's not always going to overestimate or underestimate, and sometimes it's going to be pretty close. But on average, if we're looking at the sampling distribution of a correlation, right? What we're going to do is sort of across, sort of say, samples of 100 and row. This is the population. This is the statistical notation for population correlation. Is this p, this small rho, and say is 0.30, right? So x and y are correlated in the population 30. This is our hypothetical thing. For n equals 100, the correlation between x and y, so the average correlation is probably going to be pretty close, okay, at samples of 100. Sometimes we're going to get samples that are overestimating, sometimes underestimating, but on average, with samples of 100, we're probably going to be pretty close. But if I drop this down and I say samples of 20, right? This is probably going to be something, I don't know, let's say 0.33, right? So what ends up happening in small samples, if we're just calculating our Pearson product moment correlation, it's going to it's going to overestimate the correlation between these two variables. Okay, because again, if I've got a set of scores, right, and I've got that, right? What's that correlation going to be? Pretty strong, right? This point is dragging this correlation coefficient to a much greater extent if we've got 10, 15 points than if I go through now all of a sudden I've got a correlation that looks something like that as opposed to something like that, right? And so this is the problem. When we're working with correlation coefficients in small samples, our Pearson correlation that we get from any of our statistical packages, it's a bias coefficient. It's going to be systematically too big. Just like we talked about, our effect size G is biased. It's going to overestimate, right? And so if you're working with small samples, you can create a small sample correction here by taking your adjusted R or your adjusted coefficient, taking 1 minus the square of your Pearson correlation times n minus 1 over n minus 2, going through, and what that's going to do is it's going to pull that down. It's going to make an adjustment on that coefficient to sort of help address some of that bias. Now, if we're working with large samples, which is technically what we should be doing with correlation and regression types of analyses, we don't have to worry about this too much. It's going to take care of it on its own. But if I have, say, an experimental study, and I get a sample of 18 people, so what Adam's working on his dissertation, and in his trauma group, he's got a trauma group and a control group, and in this trauma group, looking at the correlation between a couple of repeated measures is 0.85 or something like that, but he's only got like 17 people in that sample. I'm not confident that those two measures are correlated that strongly. It's likely, or it's possible that that's an overestimation of the strength of that relation just because it's a small sample. Right now, as that sample size starts to get bigger, you're working with samples of, I don't know, 50, 100. I mean, you can do this on your own. You can go through and look at your correlation coefficient, then calculate an adjustment, see how much of a difference it makes, right? As your samples start to get larger, the adjustment is going to be smaller and smaller. So, you know, if you've got something that's a noticeably small sample, you might, if you want to be conservative, think about this. But if you're getting into sort of larger samples, don't have to worry about this too much. You'll have a sense for what we're talking about when we're talking about bias statistics and what makes a statistic bias. I'm not saying that every time, right? Sometimes I might have a sample that wildly underestimates my correlation because I didn't get a lot of variability or anything like that, right? But on average, in small samples, our Pearson correlation is going to overestimate the true relation between X and Y in the population. Yeah.
So does SPSS automatically correct for this?
Nope.
Is there a way you can do SPSS?
No, not in SPSS, not that I know of in SPSS. It's possible. I don't know all the nooks and crannies of SPSS, but you prove yourself to be very adept at calculating, reading calculators. I mean, this is a pretty easy thing to program in Excel if you just wanted to go through and just punch in and see kind of what that difference is going to be, right? And if you were doing this in your research, no one does this. We should. We don't, right? No one wants to sort of downgrade their effect sizes and their correlations and things like that. But something to be aware of as you're evaluating your own research, evaluating other people's research, right? I have a sample of 20, and I'm super jazzed because X and Y are correlated, 0.3, and it's statistically significant. And I'm excited about that because I found a significant correlation in a small sample. Like, well, maybe it's also probably an overestimate of what that's going to look like in a larger sample, right? So wanted to take that into account and sort of use that to think critically about your results, the results of other people's stuff, and things along those lines. Other questions? All right. So Pearson correlations, So this is how we get our correlation coefficient. But oftentimes what we want to know is this statistical coefficient reliably different than 0, right? We want a significance test on it. And so if we're running our significance tests for our correlations, our null hypothesis is going to be rho equals 0. Again, this is just our indicator of our population coefficient. And our null hypothesis is that the association in the population is going to be 0. Again, if you're telling me about this, tell me what the population is and the correlation and the association of what and what. So you're just flexing those muscles. And the alternative is, or we could also say that x and y, whatever those variables are linearly independent. Right? If you want to just change up your the way you're saying this, which I do encourage you to do, it just kind of helps you gain a little bit more flexibility in how you're thinking about things. My null hypothesis could be that in the population, variable x and variable y are linearly independent of one another, not related. Right? This linear thing starts to become important too, because my correlation coefficient is a test of linear variation of x and y. Right? It doesn't say, you know, the association in the population is 0 is a little bit misleading, because I could have something that has sort of that inverse quadratic and there's a very clear association. It's just not a linear association. If I'm testing it with a correlation, I am testing a linear association, right? So not that you have to specify this in everything that you ever do, but something to think about in terms of what we're saying with this. Our alternative hypothesis, or alternate hypothesis, says that the association in the population is some non-zero value, right? It's not 0, I don't know what it is, it's just something that's not 0, and that x and y, or x and y hold a linear relation to the population, something along those lines, okay? So when you're stating this in your assignments, if I'm asking you to do this, make sure that you're sort of putting in other stuff, telling me what the population is and sort of what the measures are and things along those lines, just so sort of refreshing your brain on that stuff. Now, how do we test our correlation coefficient? What's the statistical test we use, right? Remember that if we want to have run a hypothesis test with any type of statistical coefficient, we need to know what the sampling distribution of that coefficient looks like. And what we know is that our Pearson correlation, assuming a null value of 0 in the population, our correlation coefficients follow a t-distribution with n-2 degrees of freedom. Okay? So if I'm testing x and y, right, and x and y in the population are not related, right? In the population of humans, this is literally 0, right? What I will find is that on average, in samples of, let's say 100, that my average correlation is also going to be 0, but is my sample correlation always going to be 0, Evelina? Even if the population value is 0?
No.
No, it's not, right? Sometimes I'm going to get a negative correlation, sometimes I'm going to get a positive correlation. As this sample increases, sort of the variability in this, my sample size increases, the sampling distribution of that correlation coefficient is going to get a lot tighter, right? But for small samples, say sample size 20, I might sometimes get a correlation of 0.2, even though these things aren't related in the population. I can sometimes get a correlation of negative 0.2, even though there's nothing in the population, right? But what we know mathematically is, assuming the null hypothesis, the sampling distribution that we should expect from R is going to follow a t-distribution with n-2 degrees of freedom. Okay, this is nice. This is convenient because we know what t-distributions look like. We've used them a lot, right? So we can go through and use this t-distribution to start running a hypothesis test to see, assuming that the null hypothesis is true, what's the probability of me obtaining a value, a correlation coefficient at this level or more extreme, right? This is where our p-values start to come in and all our testing starts to come in, right? So getting our test statistic, or our t statistic from our correlation coefficient is actually pretty straightforward, right? We take our correlation coefficient, multiply it by the square root of n minus 2, take that over the top of the square root of 1 minus, take that test statistic compared against a critical value at n minus 2 degrees of freedom, and that's going to give us our p-value for our correlation coefficient. Questions? Kind of see how that's working? This is nice. It's easy. We don't have to come up with a whole new distribution for a new statistic. Turns out that our Pearson correlation just follows a t distribution with t minus 2 degrees of freedom. Questions about this? Cool. All right. So, another thing to remember is our correlation coefficient also conveniently measure of effect size. This is nice because what it ends up happening is our point estimate that we're testing for the strength of association also is just a really nice convenient effect size that we can go through and start gauging and assessing the magnitude of the relation or expected relation of the population. So again, our Pearson correlation is going to be an estimate of the population correlation. It's not going to be exactly the population correlation, but based on our best, based on the data that we've collected, we're saying that this is reflective of, in general, a small population effect, a medium population effect, a large population effect. So correlations of 0.1, small effect, 0.3, medium, 0.5 is going to be a large effect. What's also nice, for the purposes of meta-analyses and just general interpretations, the correspondence between Cohen's D and our Pearson correlation is straightforward. I can go through and I can calculate, if I am looking through a paper and they're reporting a correlation coefficient and they're looking at sort of the relation between income and gender, right? And they report that as a correlation. I'm like, boy, I wonder what that is in terms of so the average distance, right, between income across or pay across men and women. Correlation is nice, but maybe because I'm looking with a group thing, I might want to calculate a D for that because that gives me difference in terms of standard deviation units. I can go through and from R, I can calculate D. Or if I have a D, I can go back through, calculate R from that, right? Jump back and forth between these two metrics easily. And remember, small Cohen's D, 0.2, right? 2/10 of a standard deviation across groups. Medium, about a half standard deviation. Large, 0.8 of a standard deviation across these two groups, right? So whatever you want to be using this for, we can sort of transfer easily back and forth. Yeah.
Why do you use Cohen's D?
Yeah, it's a good question, right? We'll get into this, I guess, spoil the surprise. I can correlate, a special type of correlation that actually is identical to the Pearson correlation, a dichotomous variable with a continuous variable, right? I can assess that in a correlation, right? And that tells me how the strength of the relation between my dichotomous variable and my continuous variable, right? And so someone might report that as a correlation, right? But maybe for me, I've identified that as, I can also look at that as a mean difference, a standardized mean difference, and that's more consistent with kind of conceptually how we think about D. And Laura has a study looking at wage discrepancy in men and women, has reported that as a D, but this other study has it as an R, and I want to see kind of how that, I can start moving back and forth between these two and do that easily. Or if I'm running meta-analyses and I have a bunch of different studies that have used a lot of different methods, and so their effect sizes are all sort of different, what I might want to do is convert those effect sizes to a common effect size R so that I can go through and compare things, right? So it just allows you to move back and forth based on whatever conceptual presentation that you want to provide. it's a function of communication and being able to compare things. Right? There's not necessarily one that's right or the other is wrong. If I'm working with like a means-based analysis and I'm working t-tests, D is nice because I have a nice interpretation that I can say, telling me the units of difference in standard deviations, right? And that gives me something that's nice to compare if I'm just looking at two groups. I could convert the correlation of depression and PTSD to a D value, and that can tell me whether it's small, medium, or large, but I don't know how to interpret. I can't attach a practical, it's hard for me to attach a practical interpretation of that because D is developed as sort of a difference between two groups in standard deviation. I can do it, but I would argue it's less meaningful and less interpretive. It has less interpretive value if I were to do it, right? So it just kind of depends. Right? So just wanting to know how you can move back and forth between these types of statistics and then choose the presentation that's going to make the most sense to you. Other questions on this? All right, cool. Another thing to be aware of is we can take our Pearson correlation and we can square it, right? If I square my Pearson correlation, what this is going to give me is a proportion of variability, of shared variability in X and Y. Okay? So if I have a correlation of 0.3 and I square that, what does that give me? What's 0.3 squared?
0.09.
100. Are you not wanting to? I don't know.
Oh,
What?
I said 0.09.
Yeah, I got it.
I said 0.9.
Oh, did you say 0.9?
Yeah.
Oh,
I didn't say it very loud.
Okay, I didn't. Just like give me like a 10 side eye. I was like, you don't have to calculate if you don't want to, I guess. Yeah, 0.9, right? So if I've got a correlation, X and Y are correlated 0.3, right? I can square that, and that tells me that about roughly 9% of the variability in X and Y is shared, right? We can talk about the variability of X and Y attributable to variability in X. That sort of assumes that there's some sort of causal relationship going on there, which you want to be careful about. But basically what that squared coefficient is telling me, so how much shared variability is there in X and Y? To what extent is this variability in Y sort of common with variability in X or shared variability in X? Oftentimes we're saying variable in our outcome that's attributable to our predictor. Again, that's using some causal language. People usually won't get too upset about that within this context, but it's just giving us a proportion of shared variability. And this is nice, right? So it says if I know, I can account for X proportion of variability in PTSD by knowing variability in depression scores or something along those lines, right? Again, thinking about R and R squared as measures of association in terms of effect size, right? These are measures of standardized difference. R's and eta squareds and partial eta squareds and things along these are measures of association. We can move back and forth between these. It's just sort of how do we want to present this information. And so small benchmarks for variability, small, medium, and large. This is 1% of the variability, talking about that as a small effect, 9% is medium, about a quarter is a large effect that we're talking about here. Again, remember when you're making interpretations, please exercise practicing like literal conceptual interpretations as just opposed to saying things are small, medium, and large, because that doesn't require a whole lot of thought. Also remember that this is very, very rough benchmarks, right? If something is, if I get a correlation of 0.28, probably not going to call that a small effect, it's a small to medium effect, right? If it's 0.12, I'm just on the small end, right? But again, Cohen very explicitly said, do not use these as bright line benchmarks, and we immediately did exactly that, right? So wanting to be flexible in terms of how you think about this stuff. Okay, yeah.
So if we're doing like a write-up,
You can if you want to. I don't. It's sort of up to you. And it's up to, like, what makes the most sense, right? Is there something that adds to my conceptual understanding of this, right? So if I have a correlation of 0.1, right? I say that's consistent with a smaller vector, right? I mean, I could square it and say, specify that this accounts for 1% of the variability of my outcome, but unless there's some reason I want to highlight that, I don't know that I would necessarily talk about that, right? I mean, it just kind of depends on what story that you're trying to tell, right? Again, statistics are just a means for us to communicate information to other people, and so we don't want to sort of say hard and fast rules like, oh, if I'm going to interpret this, this is always the way I have to say it or present it or things along those lines. We want to use this flexibly to make points, emphasize things in our data that we think are important, right? So if I got a correlation of, 0.75, someone square 0.75, tell me what that is.
0.5625.
0.5625, right? So obviously people are going to recognize that the correlation of 0.75 is strong. I could go through and farther and say, so basically over 52% of the variability in X is shared with variability in Y or attributable variability in Y, right? That sort of interpretively kind of carries a lot of weight. Like, oh, wow, right? Or, in sort of my trauma stuff, people are interested in doing factor structure of PTSD or something like that, right? Like, oh, this is my 8-factor structure of PTSD, which is nonsense, right? But you go down through and you look at correlations between factors, right? And Haley, can you square 0.9 is 0.81, right? Say, yeah, that's cool. Your unique factors have over 80% shared variability in their outcome. Those aren't different constructs. Those are the same thing, right? So wanting to be able to move back and forth and know how to change, sort of adapt your interpretation to sort of make clear statements and try and help communicate information to people. So unless I tell you exactly to do something this way in your assignments, you can kind of play around with things. But thinking about like, oh, could I square this? Does that tell me anything useful about this? Like, there's another way to look at it, but so I'm fine with just reporting this, or like, oh, this is important for people to see that, yeah, even though there is a significant correlation at the end of the day. So I've got a correlation of 0.1. Let's say I've got a really large sample that's 0.09. 0.09 is my correlation. It's statistically significant. Say these two things are statistically significant, but functionally less than 1% of the variability in the outcome is attributable to X. So we're not going to worry about that a whole lot, right? So different ways of going through and talking about these relations to sort of make your case.
Is there any way to interpret R beyond just saying it's a large effect size?
Just a correlation of coefficient of covariance. It just lets you know sort of how strong those two things are related. And R is a very, very useful effect size, right? So, if I say, oh, the X and Y are correlated 0.2, I generally have a sense for sort of the extent to which those two things are correlated with one another. And so just this in and of itself conveys information. This is just another thing we can do if we want to sort of expand on that. Other questions? All right. So assumptions of our correlation coefficient. Now if you read, Howell has a really nice section on correlation regression in this text. Tabachnik and Fidel. Did anybody jumped in any of the Tabachnik and Fidel chapters yet? Yeah, okay. It's an easier read than Howell. It makes multivariate, graduate level multivariate statistics accessible. It's a really, really nice text, and again, it will help as we start to get into the weeds of this stuff. It'll help provide additional looks and explanations and things like that. So do sort of go through and take a look at that. But one of the points that Howell makes is if we're just using R as a descriptive measure, that is a sense to the extent to which X and Y are related to one another, we don't really have to worry about any assumptions. But if I want to run a statistical test on it, right? If I want to say, is this correlation significantly different than 0? Now all of a sudden, I have to start worrying about assumptions, right? Because our assumptions are the rules of the game, right? Assumptions tell us like, oh, well, if everybody's playing by the same rules, this is the interpretation that we can have. But as soon as we start drifting off into, we've got 12 men on the team instead of 11, and someone's using a different goalpost than what the other person's using, all of a sudden, it's hard to tell sort of exactly what's going on. We lose confidence in our statistical inferences, right? And so if we're going to have run hypotheses tests with our correlation coefficients, some things that we need to start thinking about. So if we're going to run a hypotheses test with our correlation coefficient, our test of R as an estimate of our correlation coefficient as an estimate of rho assumes that my variables are sampled from a bivariate normal distribution. Okay. So what this means is we have to start thinking about things in a three-dimensional space. Okay. So everybody look at me. Do this. Okay. This is your x and your y axis. Okay. John, I don't see your hand up here. There we go. All right. Excellent. Kate, throw it up there. Let me see it. Leave game sign. All right. Throw that middle finger out there like that. Okay. This is your three-dimensional space here. Here's your x. Here's your y. If we're looking at this, look at this. Here's my x. Here's my y. And then we're looking at this stuff in three-dimensional space right here. Okay. So what we want to say, if we've got a bivariate normal distribution, we're saying distributions of x's and y's are kind of scattered up here. It's kind of like a pile, right? And what we would expect with a binormal distribution is something that we were calling a conditional distribution of x and y, right? We've been talking to this point about looking at distribution of x scores and distribution of y scores, okay? And we can say, oh, it's normal, it's not normal, it's skewed, it's kurtotic, or we have outliers, sort of whatever, right? But when we start talking about conditional distributions in bivariate space, we're saying the conditional, if I'm talking about the conditional distribution of x, I'm saying that the distribution of x values for any given value of y is going to be normal. Okay, so if this is my three-dimensional space here, what I'm saying is I go through and I want to look at the distribution of x scores. When y is a -1, I want that distribution to be normal. Okay, so if I go through and I cut this and I create a plane on this bivariate normal distribution, if I go through and slice it, I would say I'm going to think about this as taking your SPSS set and restricting it only looking at the distribution of my outcome for people who have a score on x of -1, right? If I look at the distribution of y scores for everybody who has x of -1, I want those scores to look. I want those scores to be have a normal distribution. Same thing if I were to cut this and look at the distribution of y scores for everybody who has x of 0. Same thing. I would still want it to be normal. Shape's going to change, but I want it to generally follow a normal distribution. Okay? Same thing. My conditional distribution of y. My conditional distribution of y for any value of x is normal. So if I go through and I say for x equals 0, I'm going to go through and slice this. So for everybody who has an x of 0, what's the distribution of y scores when x is equal to 0 here? Okay. So these conditional distributions are saying not just for, and so this is how we think of like our, and you've already done this, you've already actually looked at conditional distributions. For our t-tests, right? How do we go through, and if we're screening distributional assumptions of our outcome for our t-test, what do we need to do first?
See if the populations we're interested in is distributed normally.
Okay, so we're looking at normal distribution, but as we're going through, what do we look at the distribution of our outcome for everybody? What do we do first? Remember? We look at it for each group, right? We split their file, right?
Yeah.
So I look at this distribution. So is the distribution of scores normal for men, and is it normal for women? Is it normal for this group, and is it normal for that group? Is it normal across each one of these conditions? Essentially what we're doing here is we're looking at a conditional distribution, right? Because we're looking at, are scores normally distributed? And say now we have an infinite number of groups, right? The concern is for any sort of given value of x, do we see a normal distribution of y? And for any given value of y, do we see a normal distribution of x? Okay? And so in this three-dimensional space, you can start thinking about this as starting to take slices, and no matter where we slice this, we want to see a normal distribution of scores. Okay? And so have asterisked this here, distribution of y values for any value of x. This is the assumption in regression, technically, right? Technically, we have no distributional assumptions of x for our predictor values in regression. We end up functionally having to have them because of other things that we violate, but technically, this is the difference between regression and correlation. Is technically for a regression model, we have no distributional assumptions of our predictors, only our outcomes. We lose that because of basically the violation of our fixed effects assumption, which we'll get into, but just from a technical standpoint, so just want to make that differentiation here. So these are our conditional distributions. Conditional distributions are kind of hard to wrap your head around, but people kind of see what we're talking about in terms of conditional distributions. Okay. Another thing we need is, if I have a bivariate normal distribution, all my two conditional distributions of x and y are normal, and then also my marginal distributions of x and y. Marginal distribution of x and y, this is just saying collapsing across all values of x. So ignoring x is y normally distributed, is x normally distributed, right? And this is just running your histogram of x and y, just with everybody collapsed together, okay? So marginal distribution, this is everybody. Sort of the distribution of y across all values of x, the distribution of x across all values of y. When we get into our conditional distributions, this is saying for everybody who has a value of 0, what's the distribution of y? For everybody who has a value of 1, what's the distribution of y? 2, 3, 4, 5, 6. We want the distribution of y values across any given value of x to be normal. Same thing if we swap it around. We want the distribution of x scores to be normal across any given value of y. Okay. And if these things hold, then we have a bivariate normal distribution, and we have sort of adhered to our basic assumptions of our Pearson correlation. So this is kind of heavy stuff. People should have questions about this? Cool. All right. So, question. If the null hypothesis is true, what do we get? What would the shape of our bivariate normal distribution be under assuming that the null is true? And think of this in three-dimensional space, right? This bivariate normal distribution here is indicating, it's suggesting a correlation between x and y, right? What if x and y are uncorrelated? What is that distribution? What's this bivariate normal distribution look like?
Would it be two-dimensional?
It's not going to be two-dimensional, but you're kind of getting that right direction. What's that?
Flat, there's less of
Not flat. Kind
a super round.
of close, yeah. Yeah, not rounded necessarily, but like an anthill, right? It just kind of spread out sort of equally in all the same directions, right? So it's going to be the same type of normal. You see, for this correlation, these two variables have a bivariate normal distribution. It looks like someone poured sand in kind of a line, right? So you get sort of this, but it's sort of going, it's still bivariate normal, right? No matter how we slice it, we're still getting sort of normal curves. But we see that this is kind of spread out. So like, again, someone took a pile of sand and just sort of drug it out like that. If we had true, if x and y are truly unrelated, as we would expect under the null hypotheses, it's just like someone dumped a pile of sand, so it's just right down the center, and so any direction is just kind of going to flow out here, right? So again, thinking about this in three-dimensional space, how those stack up on the x and y So that's another way to start thinking about, sort of kind of solidify your mind on kind of what's going on with this bivariate normal assumption. We're going to go through and talk about this when we do the regression and sort of starting to think about running our assumptions of that. Because if you thought means-based analyses were fun, we get to that part of it. So, okay, questions? Yeah.
So if we were like screening for this SPSS, would just be checking the standard for each one?
No, you don't have to do that. That's actually testing this bivariate normal distribution ends up being kind of complicated. We'll take a couple of shortcuts and say, under these conditions, we're making an assumption that sort of your distribution of scores are normal. Actually, when we get into regression, our assumptions actually aren't technically about the scores themselves. They're about our residuals, sort of our errors. And so we'll get into how we actually start to test that in SPSS moving forward. I'm not going to make you do any screenings for our correlation stuff, but important things to know. Questions on this? All right. So correlations in SPSS is pretty easy, straightforward. We go analyze, correlate, bivariate. If you're punching it into syntax statement, this is what it would look like. Again, you probably just paste that in. Number of variables, you can dump as many variables in there. It'll just make you a massive correlation table. Here, just including our PTSD total and then our measure of social support. This is just sort of some of our lab data, how we go through and do that. Output, pretty straightforward. It's going to give us a correlation table where we're getting a correlation of negative 0.274, and it looks like that's statistically significant. And we have 325 individuals with both our PTSD and our social support scores. Layla, can you tell me how we interpret that correlation? What is that suggesting to us?
That as the CAP score increases, then SPSS score increases.
Yep, and what does that mean?
That means that as PTSD severity increases, social support increases.
Yep, perfect. So we've got an inverse correlation here, suggesting is one variable gets bigger, the other one tends to get smaller, right? You've got your calculator. Can you square negative 0.274 for me?
It says negative 0.075, but it should just be 0.075.
Did you give you a negative on a square?
It's because I didn't put it in parentheses.
Oh, okay.
Yeah.
So what's the absolute value?
0.075.
0.075, right? So 7.5% of variability in PTSD scores attributable to social support or vice versa, however you want to just share here. About 7.5% of variability is being shared across these measures, right? That's we see that this is statistically significant. What is it, if we see, Kate, that this is statistically significant, what does this tell me?
That
In a very literal sense.
That the likelihood of you getting an inverse. Well, yeah. One second.
No, you're absolutely right. If we're gonna,
Of you getting that is significant.
yeah, and so we don't know, it's not zero exactly, right?
Yeah.
It's sort of carried out to something. But if we're not sort of looking at so we rejected the null hypothesis, and what does the rejection of our null hypothesis tell us in this circumstance?
That there is a difference between the CAP score and PTSD, or no, that the correlation between CAP score and PTSD is not equal to zero.
Exactly, and this is an important thing to recognize. All this says, right, is that the correlation, based on these data, we have sufficient evidence to conclude that the correlation between social support and PTSD is not zero. Is that important or interesting? I don't know, right? And again, as we're going through, wanting to be careful that we recognize what we're actually testing with these analyses. All this is saying is that the correlation isn't zero. I've also got over 300 people in this sample, right? Looking at this, what's the magnitude of this correlation? What's that?
Moderate.
Yeah, it's getting a little close to moderate, right? But in this data set, we've sort of been working on this project for a long time, put a lot of work into collecting these data and running assessments and things like that. We've got enough power now that correlations in the order like 0.12 are statistically significant, right? And again, that's statistically significant, but all it says is that actually the correlation, based on the data that we have, we can conclude that the correlation between X and Y in the population is not 0. And whether or not that means anything or is interesting, who knows, right? So again, one of those things we wanted to remember that if we're looking at our statistical tests, and we reject the null hypotheses, 99% of the time, all it's saying is that some value isn't equal to 0. Whether or not that's meaningful or not, we have to sort of bring our conceptual understanding of what's going on in the literature and all that type of thing, right? So just be very careful. So we talk about this as statistical significance. This says nothing about practical significance, about whether or not anything's meaningful or not, right? So just wanted to make sure that you're being careful in terms of evaluating this stuff critically. Okay. All right. So that's SPSS in Stata. It's also easy. Down here, we just said PW core, CAPS, MSPSS, and then tag on significance if we want to have it tell us statistical significance. Right here, we get the exact same coefficient, the exact same p-value. So just a different way to go through and take a look at this stuff. So, questions about our correlation stuff up to this point? What time is it? What is it? 3:24? Okay, cool. Let's stop, take a break, and we'll come back and we'll finish up with the rest of the stuff. The second part of the show is fun things we can do with correlations that are probably less good than other things we could do in terms of analyses, but things we want to be aware of, ways we can go through and start manipulating these correlation coefficients to start asking some different questions. So one of the things we can do with our correlation coefficients is we can go through and we can run a test of independent correlations. Okay. So in this situation, we've got two different populations. I've looked at the correlation between X and Y in population 1 and the correlation between X and Y in population 2, right? And what I want to do is I want to see whether or not there's a difference in these population coefficients, or in my estimates of the coefficient in these two populations. So my null hypothesis is that the difference in the population coefficients is equal to 0, or in other words, correlation of X and Y in this population is identical to the correlation in this population. My alternate hypothesis is that there is a difference in the population correlations, or the population coefficients. There's some non-zero value. Row 1 is not equal to row 2. Okay. So essentially, can someone give me an example of sort of what this analysis might look like in practical terms? Yeah.
So if you had like a population of people with like eating disorders, and a population of people without eating disorders, the association between like eating shame might be like different in the population of people with eating disorders and the population of people without.
Perfect, perfect, absolutely correct. So I've got people with some form of eating pathology and people who don't meet criteria for eating pathology, and I want to see correlation between sort of calories consumed and sort of subjective shame or something like that. And Evelyn, what might you expect? What might you hypothesize in terms of the difference in those correlations?
That in the population of people with eating pathologies, that higher caloric intake will be associated with increased shame.
Yeah.
Whereas in the other population, there might not be a relationship between.
Okay, right. So you're saying that for individuals who meet criteria for eating pathology, that's a separate population than people who don't have any eating difficulties. And I'm saying the correlation between daily caloric intake and shame in this population is going to be stronger than in normal people. Perfect, absolutely, right? We're looking at the same measures, we're just looking at a couple of different groups, okay? And so what we can do is we can start to go through and say, here's the correlation in this group, here's the correlation in this group. We can go through and we can compare these two, okay? Now the difficulty is is that the distribution of R1 minus R2 is complicated. Okay? And again, what we need to know is in order to run a statistical test, we need to know what the sampling distribution of these scores are. Turns out, the sampling distribution of one correlation minus another correlation is kind of funky and weird, and so it starts to complicate us running a statistical test on this. Okay? But what we can do is start to utilize something called a Fisher's R to Z transform. Okay? So what we do is we take our Pearson correlation, R, and we take that R coefficient and we use a log transform, Fisher's R to Z transform, to translate that correlation coefficient into R prime. Okay? And R prime is equal to 1/2 or 0.5 times the natural log of the absolute value of 1 plus R over 1 minus R. What is the absolute value? Tell us what we're going to do with this. John?
It'll be positive.
Yeah, it just takes the positive, right? So we drop whatever negative is on there, right? And so if we use this Fisher's R to Z transform, what we now have is we have R prime. Now R prime isn't a correlation coefficient. R prime is a transform of that is R prime, right? But what we can do is, once we have R prime, we do know and we can derive a standard error from R prime. R1 minus R2 has a funky distribution. It's hard to predict. We don't know what that's going to look like. But what we can do is we can go through and we can take the Fisher R to Z transform, get R prime, and we do know the sampling distribution of R prime, right? And we know that the sampling distribution of R prime, standard error for R prime, is 1 over the square root of n minus 3. Okay? So what we can do with this is we can go through, and instead of just taking our raw correlation coefficient for our controls and our correlation coefficient for our e-methodology folks, what we can do is we can take both of those correlations, transform them into R prime, right? And then what we can do is we can derive a Z statistic from those. And so in this situation, my Z statistic is going to be R prime 1 minus R prime 2, right? So I'm just taking the Fisher R to Z transform for my one group and my other group, subtracting those over the top of 1 over n minus 3 for my first group, 1 over n minus 3 for my second group. Okay. Does this look familiar to anybody? Okay, you're nodding a little bit. What does this formula look like?
How we would usually find a Z-score.
Not the Z-score.
Oh, is it standard error?
Getting there. What does this look like? Looks like an independent t-test. Remember, we've got two sources of variability here. We've got standard error in my first coefficient, standard error in my second coefficient. If you go back through and take a look at your t-test, you're going to look. This formula is going to look like a lot like how we've gone through and set up that formula there. So essentially, what we're doing is kind of running an independent sample t-test across, just using, instead of means, we're using a couple different correlations, right? And so if we do that, we get a Z. Our Z value is evaluated against a critical value for whatever our alpha is. We worry about is the degrees of freedom for our Z distribution. No, Z is just Z, right? What's our critical value for alpha equal 0.05 for Z for a two-tailed test? 1.96, right? So you just go through, and if your Z statistic is greater than or equal to 1.96, it's statistically significant at alpha equal to 105. Right? Then we can go through and actually calculate p-values using calculators and things like that, if that's something you want to do. Okay. So people see what we're doing with the comparing independent correlation coefficients. I've got X and Y in this group, X and Y in that group. I just want to see if they're different. Okay. Anybody have any idea of another way we could go? Or does this sound familiar to anybody? How else could we start to? So our question is whether or not the relation between X and Y is different in this group versus that group. What does this sound like? Or we're saying, does our grouping variable impact the relation between X and Y? What does that sound like?
Moderation.
It's a moderation question. this is a busted way to run moderation, okay? Limitations are, like, so if you just wanted to know, so Evelina, if you wanted to see whether or not eating shame was more strongly correlated in people with eating pathology or people who didn't meet criteria, you should probably just run that in a moderation analysis, and we'll talk about how to do this, right? Here you can't control for other types of things. This is a much more limited way of going about things. But sometimes, right, sometimes we might not have access to full data, right? I have data from X, correlation between X and Y in this paper that's using this population, and I've got my own data that has it in this, I don't have access to all this source, so I can't run this stuff. But what I could do is I could go through and see, is this correlation statistically stronger than what I'm getting here, and start to go through and run some of this stuff. So you won't use this a whole lot, but it's something that you can do, and again, it's something that's we can start to do based on pre-existing data or stuff that we've gone in sort of summary statistics to go through and start to test whether or not we have, like, boy, I've got a much stronger correlation between these two variables than these folks got. They used a different sort of sampler population. I can go through and sort of test whether or not, see what those things are different. Questions on this? Yeah, John.
I may have missed it, but do we do anything with like the standard
The standard error, we will do something with this in just a minute. This is just showing you what the standard error of R prime is. And so you'll notice that this standard error estimate is what ended up getting dropped into our standard error for the difference test here. But yeah, we'll use that in just a moment. Other questions? All right. So this is comparing independent correlation coefficients, right? This is X and Y in this group and that group. We can also test our correlation against some hypothesized value. So we talked about sort of our routine test of statistical significance just says that our correlation coefficient is reliably different than 0. But sometimes, whether or not it's reliably different than 0 might not tell us anything, or we might not care anything about it, right? Sometimes we might actually have a point estimate, right? I want to know not whether or not my correlation coefficient is different than 0. I want to know if it's different than sort of this value, right? If I've got some reference value that is conceptually, theoretically important, what I can do is I can start to set this up to actually test not against 0, but against some reference value, okay? So here, my null hypothesis is that the association between variables in the population is equal to sort of whatever our reference value is. Our alternate, the association between X and Y in the population is different than some other sort of reference value or something like that, right? Think about this as kind of calling your shot, right? And when we think about, you know, way back when we read that Cronbach and Neal paper, right? We're talking about the difference between psychological, sort of how we approach analysis in psychology versus the hard science, right? The thrust of that paper was, you know, as our samples get better and better and our methods get more and more precise, instead of increasing the stringency of our test, it actually decreases it, because our analyses are all based on whether or not something's different than 0. If we have enough decimal places, is anything ever going to be exactly 0? No, right? And so we have this problem versus in physics, right, where I have this theory, like Laura has this theory, and she's saying if I do X and Y, it should be equal to this value. Not 0, it should be this number, right? And as we start to get more and more precise, our confidence intervals start to shrink. It gets harder and harder to provide evidence for my theories to get better, right? Well, this is one way we could, conceptually, in a world, start to improve how we start to take a look at stuff, right? So I'm saying that I've got some, something that I'm expecting to increase sort of correlation between X and Y or something like that, or X and Y have been shown to be correlated over and over again, but I think if I do this or institute this manipulation, it's going to increase sort of the magnitude of this correlation, right? And so what I'm saying is if I've done this correctly, or if my hypotheses are correct, the correlation of X and Y should be reliably different than some value in the literature, right? So let's say it's a value from meta-analysis. Say across all studies, So correlation between X and Y is 0.3. But I'm saying, given this experimental group, it should exceed 0.3. It should be reliably bigger than 0.3. So what I'm going to do is I'm going to run my experiment, correlate X and Y, and I don't care if it's different than 0. I don't know it's different than 0. That's not news. But what I'm going to do is I'm going to see is it reliably different than sort of whatever this reference term is in the sort of drawing meta-analysis or something like that, right? So this is cool because it starts opening up possibilities of testing things against some value that's just not 0, right? Now, how, questions sort of the extent to which this is going to be a useful thing to do, but I think there could be options and things if you know just a whole lot about your area, and you're saying this should be different because of this reasons. What I'm going to do is I'm going to test this, and I'm going to test it against, is it reliably different than 0, because no one cares about that. Is it systematically larger or smaller than something you can see elsewhere in the literature, okay? So running this, again, using our Fisher R to Z transform. So again, we're still going to get a Z test here. But what we're going to do is we're going to take the R transform, or the Z the R to Z transform for the coefficients that we observe for our data, the correlation between X and Y, minus whatever the Z or whatever the transform is of our reference value, right? So this is, we're just going to take whatever, let's say I'm testing against a value of 0.3. I'm just going to take, if 0.3 is my reference value, and I'm just going to take the R to Z transform from 0.3, and I'm going to subtract R to Z transform or R prime for my observed coefficient minus the R to Z transform of my reference value over square root of 1 over n minus 3. What does this formula look like? That we've seen before.
Paired samples?
Not paired. Well, technically you're not correct, not incorrect, yes. What was it, sort of given sort of how we're setting this up, what is it kind of look more like? Single sample, right? So a single sample t, but you're absolutely right, I believe, because a single sample t is just a one sample t of the different scores, right? We've only got one standard error estimate because we've only got one sort of sample that we're working with, right? So functionally what this is basically it's an analog of a single sample t-test, just testing my correlation coefficient against some value that's not 0, it's against some other reference value, okay? People see kind of what's going on here. We're taking our whatever observed correlation you get, transforming that into R prime, taking your reference value, whatever that is, transforming that over into rho prime, and then over your standard error estimate gives you a test of whether or not your observed coefficient, whether or not we have sufficient evidence to conclude that your observed coefficient is likely different than sort of whatever point estimate you expected in the population. Questions about this? All right. Finally, looking at correlated correlation coefficients. It's a tongue twister. All right. What we're doing here, right? What we're wanting to look at is whether or not correlation coefficients, whether correlation coefficients that are sharing a common measure are different from one another. Okay. So let's say I have, and again, so this is a poster going to put together for ABCT, and I've got, say, hypervigilant symptoms of PTSD, right? So I'm looking around all the time, exaggerated startle, I'm just sort of cranked up, right? In models of comorbidity, we're expecting that these symptoms should be more strongly correlated with measures of anxiety than measures of depression. So in clinical stuff, all our stuff's on top of one another, everything's super highly correlated, and so people are making an argument that, well, it's not actually different things, it's all just generalized distress, right? And so I've got a correlation of hypervigilance and I'm looking at whether or not, looking at the correlation of hypervigilance with some pure measure of anxiety, and some pure measure of depression, okay? So 1, 2, 3. Okay. So what I want to do is I've got, and let's say that this hyperarousal is correlated with anxiety 0.5, correlated with depression 0.43, and then correlated anxiety and depression are correlated with each other 0.64 or something like that, okay? And my question, if the conceptualization is sort of, if this hypervigilance factor really is sort of more representative of anxiety than depression, I would expect the correlation of hyperarousal with anxiety to be stronger than the correlation of hyperarousal and depression. Right? And now in my correlation table, I can see, yeah, the absolute value is different, but is that a reliable difference? Right? Now the problem is, what I can't do is I can't just go through and use the formula that we used before to see whether or not sort of this value is different than this value, because we're not using two separate populations. It's the same group of people. Other thing that goes through and complicates this is that we have a correlation between anxiety and depression. These two measures are correlated with one another, right? So by definition, this coefficient is correlated with this coefficient, given that these two correlation coefficients both share hyperarousal, right? So what we've got is we've got a system of correlations, and what we might want to do is test to see whether or not these are reliably different than one another in a way that's consistent with our theory or our prediction, and things along those lines. So what we're, because the correlation between anxiety and depression, so the correlation between these two is going to start to drive whether or not so we get a significant test here. So we need to take the fact that these two correlation coefficients are themselves correlated. We need to take that into account and start teasing that apart and testing that stuff. Okay, people kind of see sort of what the question is here and how we're trying to tease this stuff apart. So essentially, what we're doing is we've got two coefficients, but they share a measure. There's the same measure that's going on that's contributing to both of these. So we have to address that in a way. So our hypothesis here is population value of x and y minus the population value of correlation of x and z is equal to 0. So the difference in population coefficient for x and y and x and z is 0. Rho xy is equal to rho xz, right? So again, you see here in this notation, they both have x in them, right? So that's creating a dependency across those coefficients. Our alternate hypotheses, rho xy minus rho xz is not equal to 0. Difference in the population coefficient for x and y and x and z is some non-zero value. Rho xy is not equal to rho xz, right? So here we've just got one sample. We just got one group of people who are measuring x, y, and z. We just want to see if x and y is different than x and z, accounting for the fact that they both have a common measure in there. Okay. So, looking at these dependent correlations, we can look at, so we've talked about, we've set this up as correlations that share a measure, but we can also use these same methods to take a look for a repeated measures assessment. Let's say Layla is looking at correlation of x and y at time 1 and correlation of x and y at time 2. Want to see if there's a dependency in those because it's the same people measured on 2 different occasions. We could use the same formula to go through and take a look at this. Procedures for running these analyses, so we're not going to throw them up here. Howell talks about them. Steiger has a paper he's talking about this. This Meng paper also goes through some options. This Meng paper is nice. It's in your reading list. I'm going to have you work through that, put together a calculator, things along those lines. What's kind of cool there is this not only, so we're saying x and y different, right? Is x and y, the correlation of x and y different than the correlation of x and z? They start to outline some procedures where you can actually start comparing more correlations. So instead of just 2 correlation coefficients, look and see whether or not, let's say I've got I'm interested in the correlation of A and B and A and C and A and D. Now I've got 3 correlation coefficients, right? Basically functionally providing an analog of an ANOVA model for testing dependent correlation coefficients. Interesting stuff. This is kind of cool. That doesn't really map onto some other stuff that we can do, right? So here in these analyses, I want to see whether or not these two are different than one another, and then sort of our cognition, moods, or our general sort of negative affect types of symptoms, are those more correlated with depression than the other things? Start teasing some of this apart, right? So in this first problem set, I'll have you go through, read this main paper, go through, put together correlation sort of tests, and work through some of that stuff. It's surprising how often these types of questions come up, so it's nice to have a sense for, sort of know what to ask and then maybe how to go about taking some of that stuff. Okay. Questions on correlated correlation coefficients? All right. Confidence intervals for our R, which ends up being confidence intervals for our effect size. Okay, because John, you know what the standard error for R prime is, right? We can use that now to start creating confidence intervals around our correlation coefficients, right? Anytime we're running a statistical test, want to create an interval estimate, we need to have a standard error. In order to have a standard error, we need to have a sampling distribution, a known sampling distribution. And so for R prime, we know that the standard error for R prime is 1 over n minus 3. There, the square root of 1 over n minus 3. So what we can do is we can calculate confidence intervals around R. Because R is an effect size, that means we can also calculate confidence intervals around effect size. But the nice thing is with our Fisher R-Z transform, we don't have to worry about funky calculators from Steiger and things along those lines. We can just go through and calculate these by hand. So confidence interval for our population coefficient. Now remember, this isn't going to be a confidence interval around our correlation. This is going to be a confidence interval around R prime. Right? Now, R prime isn't what we're interested in, but it's a way to go through and get back transformed into something that we want, right? So, because we know the standard error for R prime, what we can do is we can create a confidence interval around R prime, right? So we go through and we have R prime, which is our coefficient that we've transformed using our Fisher R to Z, plus or minus a Z distribution. You remember our Fisher's R to Z, this R prime transform is distributed on a Z curve, right? So taking whatever our critical value is for Z, whatever we want our confidence interval would be, right? So if we're creating a 95% confidence interval, what's our critical Z we're using? 1.96, right? So 1.96 times the square root of 1 over n minus 3. Pretty easy, straightforward, right? But what this gives me then is a 95% confidence interval for the lower estimate of R prime in the population and the upper estimate of R prime in the population. Okay. Kate, are we interested in R prime? Not really, right? So what we can then do is take that upper and lower limits for R prime and then back translate that into correlation coefficients that make some sense. Okay? And so what we can do when we back transform that is we take base E to the 2 times R prime minus 1 over base E to the 2 R prime plus 1. And what this is going to do, if you do this for the lower limit and the upper limit, this is just going to back transform and give you sort of lower limit for your Pearson correlation and upper limit for Pearson correlation. Haley, I see you thinking. You see kind of how we're doing this.
What is E? Is that something that's logs?
Yeah, it's base E is your base for your natural log. It's 2.18 something right there. So if you look at people's calculators are going to be different, but you'll see a base E. You'll see an E to the X number on there. That's just taking base E to sort of whatever power you've got. So in terms of order of operations, you're just taking, let's say, I want to get transformed into the lower limit, right, back into something. So I take whatever this number is, right, and I take it, multiply it by 2, and then take base E to that number, minus 1, over the top of base e to that number plus 1. So this divided by that, and that sort of gives me, back translates into my lower bound for my confidence interval. Then I take the same thing and sort of run that backwards to do that.
Okay.
Okay. And so, yeah, you should on your scientific calculator have an option to take base e to that, so that you're not taking, it'd be the same thing like taking pi, essentially pi to this, or sort of some other such thing, right? So that you don't have to just 314, because then it's potentially throwing your estimates all over the place. Okay. And so then what we can do is go back through and do this. So same thing, same type of principle when we were calculating confidence intervals around D, right? We couldn't calculate those directly. We had to get the lower and upper limit for the non-centrality parameter, and then back translate the upper and lower limits for the non-transality parameter back into D's. Same thing you're doing still here. Yeah.
Are, excuse me, R and rho interchangeable?
Yeah, so remember, oh.
That's
Oh, no,
cool.
that's not what I wanted to do. Okay, never mind, I'm gonna stop touching things. Yeah, so when you see rho, that's just your population estimate, right? And so remember that our confidence intervals are population estimates, or our confidence limits are population estimates. Anytime we're creating a confidence interval, we're creating an interval estimate for the actual population value, right? So yep, use those things as interchangeable. The only thing you want to be careful of is, like when we're doing this, right? So this is your observed estimate, and that's your, whatever your reference value is for rho, right?
Sure. So it's basically like mean minus mu.
Exactly,
Okay.
exactly the same type of thing. All right. Kind of get the sense of this? So this is something you do, and I think I'll probably have you go through and calculate it, sort of put together an Excel calculator for, or you just use data and go CI2, and then it just gives it to you, which is also nice. I'm making Layla use data for stuff. Nice, you can double check your confidence intervals on stuff. But so again, in this example, so we went through and said PW core caps MSPSS gives us our correlation here, which is negative 0.2741, right? And then using this command, CI2 caps total MSPSS core, says confidence interval for Pearson correlation is a point estimate. Here's my lower bound, here's my upper bound. So again, nice. So if we start to extend outside of SPSS, sort of different programs being able to start to execute things a little bit more efficiently. Now, once you go through and put together your calculator, I mean, this one actually isn't all that difficult to put together in Excel, but other options available to you there. Okay. Question? Yeah.
And then for like interpreting the confidence interval for correlation,
Okay,
it'd
yeah.
just be like the same thing, like for the true population, correlation between variable 1 and variable 2.
Yep, yep. And again, as you're this semester, as you're working through interpretations of your confidence intervals, you know, try and mix it up and things like that, right? So what I would say here is, based on the data that we gathered here, we expect for population of university undergraduates experiencing significant trauma, correlation between social support is measured through the MSPSS and PTSD symptoms is negative 0.274. Confidence interval based on these data suggests a lower bound estimate to populate, or a lower bound value in the population of negative 0.37 and a upper bound of negative 0.17, right? Again, so just going through and one, identifying what population we're drawing this from, and we're generalizing to what our measures are, and then identifying so that we're expecting. So this is a point estimate, right? This is our best guess. I know that this isn't exactly correct based on the data that I've collected. We're saying anything between negative 0.37 and 0.17 reasonable guesses for what's going on in the population. So same thing we talked about before, just going through it, and now we're just talking about correlations instead of mean values or differences or things along those lines. Yeah.
For the second confidence interval formulas, like the AC minus 1 lower, AC minus or plus 1 upper.
Yeah. Which, I'm sorry, John, which one were we talking about? Oh, right here?
Yeah.
Yeah.
No.
Yeah. So this right here is that. That's what you get at. So we're starting with the upper and lower limit of R prime, and then we just have to back translate that to get sort of actual correlation coefficients. All right. Power analyses. In G power, this is pretty easy, straightforward. What we're going to do is go in G power and choose exact, and you'll find correlation bivariate normal model. That's what we're assuming. Two tails, right? We want to test sort of our effect size. We're assuming in this example a medium, a moderate correlation of 0.3, alpha 0.05. I want to say power is 0.8. My correlation, my population correlation under the null is 0, right? And so this is saying I need 84 people to detect a medium effect, a medium correlation, right? But this should be important to think. I mean, so this is an example, and then you can go through and there's other things you can play around and find and things like that. But in terms of thinking about planning and research, right? To adequately power a sample, to have an adequately powered sample to test a medium effect, you're getting close to 100 people in order to be able to test that at power, right? Now, where our effect size is in most of psychological science. Small, right? We're generally talking about small effects. So I mean, just this, I'm demonstrating this to show you kind of how you go through sort of get a power analysis for correlation coefficient in G power, but thinking about sort of where our samples typically are when we're trying to detect any type of effect. We're generally massively underpowered, right? And hey, this is in experimental research with problems with replications and things like that, right? If I've got samples of 20, 30, and I'm looking at correlations, and I'm excited because I found a correlation between this sort of thing that I was looking at, right? But we know that that correlation coefficient is a biased estimator, particularly at small samples. It's going to overestimate, right? And so again, if we start to understand sort of what's going on, it's actually not surprising at all that we have a hard time replicating some of this stuff, just because we violated stuff and ignored sort of warnings and things along those lines. And so once we get, 84 is a pretty decent sized sample, particularly if we're trying to do experimental stuff and run people through a bunch of manipulations and things along those lines. So keeping this in mind when we think about, how many people will I need to sort of reasonably test this effect? Probably more than you think. Okay. All right. Or you just run your sample at 30 and just hope that you wildly overestimate the population coefficient and then just call it good with no significance. Okay. All right. Questions about any of this stuff? Okay. We're going to move on to a different correlation called point by serial correlation. Point by serial, so up to this point we've been looking at continuous measure of X, continuous measure of Y. Right? We've got continuous trauma symptoms, continuous measure of social support, looking at whether or not X and Y are correlated with one another. What we're going to do now is talk about a different situation where I'm working with a dichotomous X and a continuous outcome. Okay? And if under these circumstances, what I've got is my X variable is categorical, it's 1 or 0, 1, and then I'm looking at the relation between some continuous outcome Y. Okay? What's nice is this point by serial correlation is mathematically equivalent to our Pearson correlation. Okay? We don't have to do anything different. We estimate it the same way. All that's happening is we're looking at the relation between a dichotomous predictor and a continuous outcome, if we want to use that, or just the association between a dichotomous variable, continuous variable. Mathematically equivalent to our Pearson correlation. And what our point by serial correlation is, it's estimating for when my dichotomous variable is 0, average value of Y there. When my dichotomous variable takes a value of 1, average value there, and we're just drawing a line between that, right? Scatter plots of point by serial correlations are often not terribly informative. It's just this column and that column. But what's going on in terms of drawing this line is taking, estimating the mean value of y at when x is 0, the mean value of y when x is 1, and just drawing the line right there. Okay. People see kind of where that line is coming from, and in general why a scatter plot of a point by serial correlation isn't often terribly informative. What it does do though is it shows you, it gives you a nice graph of variability in y, or variability across groups. Essentially, this is, if you ran a histogram of y at 0 and of y at 1, this is like you looking down on it, right? It's just kind of the spread of scores there, the spread of scores there, and this is just the lines running through the mean of these two. If we square our point by serial correlation, continues to represent the proportion of variability in y attributable to variability in x. Same thing as our Pearson correlation. I can go through and I can take my squared by serial and interpret that as the proportion of variability in my outcome that's attributable to my dichotomous factor. This is interchangeable. I can use it the same way. Okay. And so here, what do I got? I got a graph of pain severity, or excuse me, this is whether or not people have chronic pain or don't have chronic pain, and their PTSD scores. So these are motor vehicle accident survivors, and we're seeing a correlation of 0.38 in terms of this, right? And so as you might expect, how could we also test this question, whether or not chronic pain is related to PTSD symptoms? What else could we use? The t-test, right? So people with and without chronic pain in terms of post-trauma symptoms after a car accident, right? I could use this with a t-test, and this is just looking at mean difference here, mean difference here. With a point by serial correlation, I'm not asking this in terms of mean differences, I'm just saying, is there a relation between chronic pain status and trauma symptoms here? Okay.
If that's exactly the same as Pearson, why do we differentiate it? Is it just to describe the variable?
Sort of historically, sort of differences in the way sort of you go through and calculate things in the formulas and sort of the development, but it's functionally mathematically, it's all the same, right? So what I want you to be aware of sort of terminology and things along those lines. So it happens sometimes, like you can't look at that with a correlation, you have to use a t-test. Get out of here. It's the same thing. It's not any different, it's exactly, it's mathematically the same thing. Don't tell me what I have to do. So just being able to sort of recognize the differences here, right? So, and then also if you see someone talking about a point by serial correlation, you know that they're talking about the relation between a dichotomous variable and a continuous outcome.
So the outcome will be the same even though the formulas are different, technically how you get around to it.
Yeah, it's the same thing, you know, thinking about how like ANOVA kind of developed in its own sort of area, and then regressions over here, and then at some point something like these are mathematically the same thing. They're identical, right? And so our point by serial correlation identical to R, and also consequently statistically identical in terms of your p-values in terms of to your independent sample t-test here. So I can take my point by serial correlation. If I want a test of my point by serial correlation, so I've got a point by serial correlation of 0.379, right? If I want to run a hypothesis test on this, I run this with the same way that I ran my Pearson correlation. I take my point estimate of my biserial correlation times the square root of n minus 2 over the square root of 1 minus the square of my correlation coefficient. That gives me my t-statistic. I test my t-statistic, compare my t-statistic against a critical value of t equal to n minus 2 degrees of freedom. This formula is exactly the same thing as we presented for Pearson formula. It's just we're substituting our biserial for sort of our Pearson product model correlation. Same thing. We also see that as we're talking about this Pearson or this biserial correlation, direct correspondence to our independent sample t-test. Right. So if I take if I run an independent sample t-test, right, and I take my test statistic, my t-value, and I square it, and I take it over to the square of my t-test, or my test statistic plus the degrees of freedom for that test, it's going to give me the square of my point by zero correlation. Okay? And the square of my point by zero correlation is going to tell me the proportion variability of my outcome that's true than my dichotomous factor. Right? We'll start to see how we can move back and forth between these tests and start to change sort of we're getting a different number, but it's all sort of capturing the same relationship. Okay. So because of this, our means-based tests are point by zero correlations interchangeable. The only thing that matters is how I want to present this, right? So I can talk about men and women differing in average weight, right? I could talk about there existing a linear relation between gender and weight. I can say physical weight varies with gender. These are all different ways of saying the exact same thing, right? And so depending on how I want to present this, I can start to choose, do I present this as a means-based test, like as a t-test? Do I just want to present it as a correlation? So what makes the most sense given the aims of my project? So as an example, when I was writing a paper at one point, I want to go through and look at, so I had people who had completed, or people who we had included in the study and people who had to sort of get rid of for whatever reason, right? And had a number of, sort of wanted to make sure the people who completed and those who didn't differ on a number of different sort of outcome variables that were kind of contiguous, and then had like gender in there, right? I was like, okay, well, I'm just going to go through and I'm going to test, sort of look at the whether or not there's a correlation between inclusion, exclusion, and some of these outcomes, right? And I just wanted to say no correlation, sort of the correlation, whether or not people were included or excluded, or sort of not reliably correlated with any of these things, right? And I had something like, well, you can't do that. You have to t-test. You got to run a t-test. It's not important. I'm not interested in it. I just wanted to say that we don't have sufficient evidence to make a strong claim that people who were included are reliably different than people who were excluded. I just run this as a t. It's a much more correlation. It's just a much more efficient way to go through and do this, right? I didn't want to run a bunch of correlations and then run a t-test, and it's right. It's all the exact same thing, right? So, but knowing that can be helpful in terms of how we want to go through and shape things. Now, if I have a group-based difference, right, and that's kind of the big thing, I want to say that group A is different than group B, then yeah, I probably should use a t-test just because it's easier to communicate, it's easier for people to think about than saying, oh, condition is related to outcome. Well, if I try and do that, people want to know how much and what's the mean differences, because that's just kind of easier to wrap your head around. So in that situation, yeah, let's just run a t-test. But it's sort of an ancillary sort of analysis, and sort of it's included with other things. R is fine. It's telling you the exact same thing. The t-test is exactly the same, or the significance level is exactly the same. Okay. Questions about this? Okay, and so if we go through and we take a look at SPSS outcomes, so here I've got for our, this is from our data, from our assessment data, we got the relation between participant sex and total PTSD scores, right? I can run this as a correlation. Looks like these two things aren't strongly correlated. A Pearson correlation of -0.094. This is also a point by zero correlation by definition because one of my variables is dichotomous. One thing to remember is you're going through and scoring your, if you have dichotomous variables, if you're working with dichotomous variables, score them 0, 1. Don't score them 1, 2. Score them 0, 1. It just will make your life a lot easier. But if here we've got these scored 0, 1, this is my Pearson correlation. I don't need to dig through SPSS to try and find a point by zero correlation because that's it, right? Here's my test of statistical significance. But if I take a look at this and then I go out through and I look at the same data examined in terms of a t-test, right? I'll see that my test of statistical significance is identical across these two, right? This is a measure of association. This is a measure of mean difference. I get to pick and decide which one of these makes the most sense to sort of go through and report because mathematically they're equivalent. Questions about this? All right. Same thing, Stata. Here's our correlation of gender, right? Again, 0.0934, it's the same. Test of our significance, our p-value is the same. If I go down through, run this as a t-test, Again, significance test, it's the same. Mathematically, they're equivalent tests. They're not different. From a GLM standpoint, we can say we're looking at the relation between our dichotomous sex variable and an outcome. I can talk about it as differences across gender, mean differences across gender. I can talk about linear relationship. It doesn't matter. I can be flexible in how I'm sort of going through and talking about this. Questions on this? All right. Effect size for a point by serial correlation. Again, because our point by serial correlation is equivalent to an independent sample t-test, that means that our point by serial correlation also has a direct relation with D, our Cohen's D. So we move back and forth between these. So if I have a point by serial correlation, I can turn that into a Cohen's D using this formula. I take my degrees of freedom, sample 1, sample 2, multiply this by my point by serial correlation here, sample 1, sample 2 here, go through giving my test statistic here. What we can then do is once I have my effect size, I can go through and use the t-statistic that I got from my point by serial correlation, and then use that to go through and develop confidence intervals around D if I wanted to, right? So I compute T for my point by serial correlation, right? So I get my test statistic, and then I can take my test statistic and plug it into my Psyc calculator to get an upper or lower non-centrality parameter. And then I can take that non-centrality parameter and back translate that into a lower for D and an upper for D, right? So basically, in theory, what I could do is I could take a look at a paper that reports a correlation between a dichotomous variable and outcome, and as long as I know the number of people they have in their sample, I can back translate that into a D coefficient. I can go through and calculate upper and lower limits of that. I can calculate a T statistic for it. This all starts to be very helpful in trying to figure out exactly what people have done in their research, because sometimes they don't do a good job of telling you all this stuff. People see the value of being able to move kind of back and forth between these various statistics. Any questions? All right. Last thing we'll talk about is our phi coefficient. Sometimes what we want to do is we want to look at the relation between a dichotomous X and a dichotomous Y. Okay? If we're doing this, technically what we're doing is we're calculating a phi coefficient. Phi coefficient, the good news, is mathematically equivalent to our Pearson correlation, right? So phi, Pearson product moment, point by serial, these are all mathematically equivalent tests. They're not different than one another, right? And again, what's nice about this is because if I want to go through and I want to look at the relation between two continuous variables, a dichotomous variable and a continuous variable, a dichotomous variable and a dichotomous variable, the nice thing is in my statistical programs, I don't have to go through and choose a different analysis for each one of these. I just run a correlation between them, and it's going to give me the right answer, okay? We also know that our phi coefficient now is a direct relation with our chi-square with 1 degree of freedom, okay? So if I go through and I can move back and forth, just like our Pearson or our biserial correlation was equivalent to our independent sample t-test, phi coefficient is identical to a 2x2 chi-square, okay? Again, these are identical interchangeable tests. And so if I have a chi-square statistic, and it has to be 2x2, right? But if you have a 2x2 contingency table and you run a chi-square analysis with that, and you want to get a phi coefficient, which is going to be a measure of your effect size, you just take your chi-square over n, take the square root of that, you do phi coefficient. Moving back and forth. This is a nice effect size for, again, your 2x2 contingency tables. As with our biserial and T, interpretation of our phi coefficient, our 2x2 chi-square, interchangeable. We can move back and forth there. So we could talk about the relation between two dichotomous variables as the association between dichotomous X and dichotomous Y. Some guy would talk about a phi coefficient. we could talk about test of independence for dichotomous X and Y. Typically, I would talk about chi-square. It's just the language that's changing, right? Functionally, mathematically, it's equivalent. All you're doing is just sort of changing how you're talking about it. Are we talking about this as a chi-square test? Are we talking about it as a phi coefficient? Easy to move back and forth between all this stuff. So again, output in SPSS here, we're looking at participant sex, coded 0, 1, and PTSD diagnosis, 0, 1, right? Again, I didn't do anything. It's reading a Pearson correlation. It's actually a phi coefficient, right? 0.14. If I run this in a chi-square, and I were to get a phi coefficient here, it's also going to be 0.14. I can request that in SPSS to get my chi-square. You'll see that your significance test is off by just a little bit, but functionally these are equivalent, right? P-value here is almost exactly the same as P-value here. It's the same thing going on. Same thing in Stata. If I ask for my pairwise correlation between gender and CAPS diagnoses, again, I get the same coefficient. If I run a chi-square, get my test of statistical significance, same thing, right? So we've been just demonstrating that these really do just all work back and forth, and so that you can go through and use these in a flexible manner, okay? So some other coefficients that we have at our fingertips, go through and use biserial correlation, okay? Similar to point biserial, but what we're doing here is we're assuming some level of continuity in my dichotomous X, okay? So if I'm wanting to look at the relation between depression and, say, PTSD diagnoses, right? I know that PTSD diagnosis is basically based on some arbitrary cutoff on a larger continuum, right? I've coded it 0, 1, but the underlying construct that I'm representing is continuous, right? And so what I do is I could go through and I could calculate a biserial correlation that's going to account for the fact that the actual construct I'm looking at with my dichotomous variable is actually continuous in nature. These can get a little bit tricky. Sometimes you need some special software to get this, but you can do that. Tetracorrelation, similar to your phi coefficient, but again, you're assuming that the underlying construct that you're measuring with your dichotomous X and your dichotomous Y is continuous, right? So if I'm running something where I'm looking at the relation between this condition and that condition, and these are sort of separate things, then cool, my phi coefficient is fine. But now I'm looking at the relation between depressive diagnoses and PTSD diagnoses, so artificially dichotomized, right? And so I can go through and calculate a tetracorrelation there. Spearman-Rowe, this is taking Pearson correlation and applying it to ranked scores, right? So it's not really continuous. I just have ranked scores, changes the level of measurement a little bit, an alternative here. And so we've gone through sort of different correlation coefficients. I gave you this sheet here. It's got, if you want to get deep in the weeds, all sorts of different ways and different formulas and different coefficients that people develop to capture certain types of things. You usually don't use these a whole lot, and you have a strong rationale for why you want to jump in and take a look at this. This is a handout that I kept from as an undergraduate in Steve Bieber's class when I was an undergrad here at the University of Wyoming, and I just hijacked it. Now I can give it out to people with proper citation. But this is nice to go through and be able to take a look and say, all right, what are different options for looking at different combinations of categorical continuous variables and sort of thinking about levels of measurement. Sometimes having arguments for why certain coefficients are going to be better than others, as opposed to just, if you've got dichotomous, truly dichotomous variables and truly continuous variables, Pearson correlations are going to go fine. But as soon as you have things that are probably not actually continuous, or things that aren't truly dichotomous, or things that I want to look at sort of 3 levels of this and that, you have other correlation or other coefficients that are probably going to be more appropriate for stuff. All right, questions? Feeling good about this? Okay, cool. Laura, what do we have? What time is it?
4:15. 431.
431, okay, cool. Questions about any correlation stuff that we've gone through to this point? All right. Not going to go through matrix algebra. I'm going to make you guys learn matrix algebra. We don't have enough time for you to learn matrix algebra. I got other things to teach you aside from matrix algebra. But if you're interested, go through slides on your own and take a look at matrix. I'm not going to ask you to be responsible for matrix algebra. This is first time I taught this class. We made people slug through matrix algebra, but it's probably not a good use of time relative to other things we could spend our time doing. So go through, take a look if you're interested. If you're a busy person and not interested, don't worry about it. If you've taken a linear algebra course or any type of matrix algebra stuff, you don't necessarily need it back. Angela, did you ever take linear algebra or any sort of matrices stuff? Okay. It's not necessary to sort of get, but if you really want to get into sort of the nuts and bolts and the inner workings of stuff, it's all based on matrix algebra and stuff like that. So particularly if you get into upper level like factor analyses and regression and stuff like that, it's all sort of based on matrices. So it's a good thing to be aware of, but probably not necessary for sort of moving forward now that we have fancy computers to do most of that stuff for us. So let's go through and take a look at starting to get into damn it. That's not the oh, I guess it is. ANOVA pairwise comparisons from Psyc 5060. This is repeaters measure stuff from Psyc 5300. So apologies for that. Angela, can you shoot me an email and tell me to fix that? Thank you. I thought I was going to have to run down to my office. That was going to be aggravating. I need to change that too because that's not correct. Okay, but what we will get into is this is correct. Going through and finishing up today with just another quick review over ANOVA and kind of what we're trying to do with these analyses. So again, at the sort of last week, we touched base with this, spent all of last semester going through talking about ANOVA designs. Remember that what we're trying to do here is determine whether or not we have mean differences across a series of samples drawn theoretically from different populations. So we have population 1, population 2, population 3. We don't know what the mean value is of our outcome across these populations. So what we're going to do is we're going to draw samples and try and estimate those to the best of our ability, right? Again, as we talked about last time, a couple different possibilities. The differences in the observed scores that we're seeing across these groups are due to just random fluctuation, or these could reflect actual differences in the actual or the true mean of each one of these different populations. What we need to do is go through and try and tease this apart, right? Are we seeing random differences due to random error, or are we seeing systematic differences? Are the differences across these groups that we're seeing, do the differences or the variability in our outcome, do those exceed what we would expect due to just random sampling variability, assuming that each, the mean of each one of these populations is identical to 0? Okay. So our one-way ANOVA hypotheses mean the population from which each sample was drawn are equal. If we're thinking about this from a GLM standpoint, we could say that there's no relation between whatever my grouping variable is and my outcome, right? I can talk about this in terms of mean differences, but I can also say, is there a relation between condition and outcome, right? Now I have 4 different conditions, and I can talk about mean differences across condition 1, 2, 3, 4. Was 4 different than 2 and 3 different than 4, and 1 different than 3, and is a combination of 1 and 2 different than 4. There's a lot of different ways to do that, right? It could be more efficient to just say it's condition related to outcome, right? Much more efficient way to go through and talk about this, right? And so here's our null. Our alternate hypotheses, there's no one alternate hypothesis, right? Our alternate hypothesis is just that at least one population mean differs from the others. Why can't I just say mean 1 is not equal to mean 2 is not equal to mean 3? Why is that not a reasonable alternative hypothesis? Yeah, it's a one way. What's the difference? What's wrong with just saying mean 1 or group 1 doesn't equal group 2 doesn't equal group 3? Anybody help her out? Yeah.
Because two groups could equal each other and
Two
just the
groups
third
could
one's
equal.
different.
So that's one version of the alternate hypothesis. But there are many versions of alternate hypotheses here, right? And then technically, I say mean 1 doesn't equal mean 2 doesn't equal mean 3. That's just one version of many possibilities that could be going on. So we would say at least one population mean differs from the others. We would say these data are unlikely, assuming that they're drawn from populations with equal means. We would say there is a relation between condition and outcome. A lot of different ways we can start thinking about this stuff. So our F statistic is looking at the variance between sample means over the variance expected if the null hypotheses were true, right? So again, if I go through and I say, I've got mean 1, mean 2, mean 3, mean 1, mean 2, mean 3, right? We start to move into variance because it's hard to start talking about mean differences because we can't sort of just get one sort of difference number. And so we start looking at our variance estimates, right? So here we're seeing much more variability across these means, and we are seeing variability across these means, right? And so, Layla, for which one of these set 1 or set 2 are we probably more likely to detect an omnibus effect? Set 1, why is that? Because there's more variability across my mean values, right? So again, in ANOVA world, we're using variability or variance as a keyword for differences, right? It's a nice way of capturing total differences without trying to say, sort of, are there individuals, or this different than that, this different than that, right? So again, for ANOVA, what we're doing is we're trying to partial variability to determine the presence of systematic differences across groups. And so remember, we're separating this into between group variance and within group variance. Again, these differences that we see across groups in our average group means can be due to systematic differences caused by the treatment or group, right? These are true population differences, or I've instituted some manipulation that's driving differences across these groups. Or we could see differences across these groups due to systematic, random differences, individual differences, experimental error, other factors that we haven't accounted for in our model. There are all sorts of other reasons outside of true differences in population means that we could see differences across our mean groups, okay? So, Laura, where do we see our between group differences here?
Different between 2 and compared to 1 and 3.
Yeah, right down here, right? So these are between group differences. This is the variability. If we're talking about between group variability, this is what we're assessing. Right now there's only 3 groups here, right? So but we can still calculate a variance or a mean squared between. This is our differences across groups, right? But again, remember that within each condition, right? If condition is the only thing that's driving variability in our scores and our outcome, everybody within a group, if they're all getting the exact same thing, okay, what should everybody's score in a given group be? The same. It should be identical, right? So that's not what we ever see, or hopefully if we saw that, then our analysis would actually fall apart. We need variability in order to run this stuff, right? And so what we're doing is we're saying that anything that's going on, any differences that we're seeing in our outcome within a certain condition is due to some type of error, right? It's the product of measured random or unmeasured influences, right? And these differences, these can be just individual differences across people. This could be experimental error, right? These can be, and this is what's important, this is could be factors that we didn't account for, right? There's some other thing going on that's driving outcome, and we're not measuring it, if we're not measuring it, where does the variability attributable to that factor go? Straight into our error term, right? And this is not good because in general we want our error term to be small, right? So this is an important thing when we're designing our studies, right? If there's some factor that's going to influence our outcome, and it's strong again, so we're going through our literature and we know that, hey, so whatever I'm measuring, this is something that's kind of important that drives some of that, it's in our best interest to include that somewhere in our model, because if we don't, all that variability is going to get dumped into our error term, and if we get a big fat error term, it makes it real hard to test statistical significance, right? Because the denominator of our test statistics is going to be massive, right? And so wanting to think about that as you're going through and planning studies and sort of thinking about this stuff. Okay? But with our one-way ANOVA, any differences that we're seeing within our groups is due to error, right? It's something that's not explained in our model. It could be something systematic, it could be random stuff. We don't know, but we're not accounting for it. So all of our within group variability is what's going on, and so this is what's going in our error term. So remember that if we're talking about this and if we're screening, here's my distribution of sample 1, here's my distribution of sample 2, and here's my distribution of sample 3, right? Now, we know that our means-based analyses are fairly robust to sort of violations of normality in the observed scores, right? But what this is saying is that if this is my mean score here, so this is my mean score here, and this is my mean score here, what's all of this going on the outside in each one of these? What are all these deviations from the average value in each one of these groups? Conceptually. It's error, right? This is stuff that we haven't accounted for. We don't know what's driving this stuff, right? And so again, we start thinking about, this starts to become important when we get into regression stuff, because we're talking about, with our means-based test, we're talking about normality of our scores, but really what we're talking about is normality of our errors, right? And this starts to become important when we start talking about regression, because we want to talk about normality in our residuals. That's what we're talking about here, right? Our homogeneity of variance assumption in our t-tests and our ANOVA. We can also talk about this, and we will talk about this, is homogeneity of errors, normality of errors, right? Because anything that falls to either side of that mean line is error. I'm not sure why people are different, because if I've modeled everything correctly, everybody should be identical. Right? And so wanting to get a sense for conceptually what's going on in terms of our within and our between and how this all works out. Okay. People have a good handle on this to understand kind of what's going on? All right, cool. So our F ratio, this is what we're using in our ANOVA designs. It's our test statistic looking at our the ratio of our between treatment variance to our within treatment variance. Is the difference that we're seeing across groups substantially greater than the variability that we're seeing, just random variability within our groups, okay? So conceptually, we're thinking about this as our observed differences, our observed group differences, over the top of our differences that we would expect under the null, right? Is even if all three of our groups are pulled from populations with the exact same mean, do we expect our samples to have the exact same mean? Nope. We're going to get some variability. There's always going to be some variability there, right? This is our sampling error, right? What we want to know is whether or not the differences that we're seeing across groups is about what we would expect due to sampling error, given that everybody's the same, or is the variability that we're seeing across groups exceed what we would expect just due to random variation across different samples or different sample selections. So we can also think about our F statistic as looking at systematic differences plus just random error over the top of random error, right? Because some of our differences that we're seeing across groups is going to be due to just random error, right? But what we would hope is if we can go through and if we're seeing no systematic group effects and the differences that we're seeing across groups entirely due to error, we're taking zero systematic effects, and we're taking random differences over random differences, we're going to get an F value about 1, right? But if we do see true differences in the populations from which these samples are drawn, or I'm doing something with this manipulation that is driving actual differences in terms of outcome across these groups, what we're going to hope to see is systematic effects plus random differences, or just the random differences that we're seeing. These two things are going to cancel out, leaving this with some systematic effects. It's going to push our F value greater than 1, sometimes much greater. Just a nice refresher, kind of getting people back in the mindset of what we're trying to do and how we're partitioning things up in ANOVA. Lauren, I don't have my phone. You give me a heads up when we're like at 5 till. Okay, cool. All right. So, ANOVA formula. I want you to remember that our sum of squares total, okay? This is going to be our total variability in our entire set of scores. So this is everybody in the sample, right? I'm looking at, in this example here, we're looking at the impact of temperature on performance, right? My sum of squares total is all the variability in performance across the whole sample, okay? I'm calculating this conceptually as the sum of the squared deviations of individual scores. This is individual I in group J minus the grand mean, and we're squaring that up, right? So our sum of squares total is 0 minus 2, 1 minus 2 squared, 3 minus 2 squared, 1 minus 2 squared, 0 minus 2 squared, 4 minus, which is basically all variability in the sample, right? My sum of squares error is my variability within each group or condition, right? This is our variability within groups due to individual differences, general error. Sum of squared here is going to be the sum of my squared deviations of individual I in group J minus the mean of group J, okay? So this is going to be the square of 0 minus 1 plus 1 minus 1 squared plus 3 minus 1 squared, 1 minus 1 squared, 0 minus 1 squared, sum those up, right? Plus 4 minus 4 squared, 3 minus 4 squared, 6 minus 4 squared, so on and so forth, right? How much are the individual scores deviating from the group mean? This is going to give me my sum of squares error, or how much I'm seeing differences within groups. And then my sum of squares treatment, this is the variability, this is the differences that we're seeing across groups. This is what's going to be remaining if I take this and I subtract my error. This is what's left over, okay? I can identify this as our sum of squares treatment. This is going to be the mean of group J minus the grand mean squared, so 1 minus 2 squared, 4 minus 2 squared, 1 minus 2 squared, and take that sum times the number of people per cell. If we got a balanced design, this is going to give us our sum of squares treatment, or we take sum of squares total minus sum of squares error. Anything that's left over is going to be due to variability across treatments. And then our mean square treatment, we just take our variance between groups divided by, take our sum of squares treatment divided by our degrees of freedom treatment, mean squared error, sum of squares error divided by degrees of freedom error. Remember that mean squared is just fancy ANOVA talk for variance. It's a variance estimate. That's all it is. Okay. Sum of squares, a measure of variability. Mean squared is actual variance. Right? And so we could even take these and sort of take the square root of the mean squared errors, and that's a like sort of aggregate, sort of standard deviation type thing. Remember that we use sometimes in terms of calculating test statistics and effect sizes and things along those lines. We'll sort of bring people back, kind of remembering kind of how we're partitioning this stuff up. All right, cool. And then our F test is just our mean squares treatment over our mean squared error. Again, here, this is our F test. Again, thinking about if there are things to control for, or things that you know do account for variability in your outcome, you want to have those in your study. Because if you don't have them in your study, they're going to get counted as error. It's going to make your denominator real big. It's going to make it harder to detect the effects that you're seeing, because there's going to be a lot of fuzz in there. It's needless. It's not random error. It's just things that you didn't account for, and maybe you should have. And so it's just going to make it harder to go through and sort of get the effects that you're looking for. Questions? All right. conclusions and interpretations. So we've got our treatment between, so we've got an F that's massive. You don't have to have a p-value, that's a significant F test. So here we'll say F value of 11.28 followed in critical region. Looks like we were testing this at alpha equal 0.01. Reject null hypotheses, conclude that mean learning scores across populations are different. In at least one temperature condition, results suggest that room temperature has a statistically reliable impact on learning. And it is going through and sort of talking about how we go through and talk about this. All right, people kind of sort of up to speed on this? All right, so moving to repeated measures. Remember that our repeated measures design, we're looking at the same group of people across one or more variables across two or more occasions. Right? What we're doing here is, it's nice because our repeated measures designs often map on nicely the types of things that we're wanting to look at in terms of things that we're doing in psychological studies, right? I want to say, all right, I want to see if this intervention works. So we start here, we take the same people and measure them after they've done it. It's a nice repeated measures design. Clinical folks, we can do treatment studies by taking 100 people and just measuring them at seeing sort of where their symptoms are, and then getting another 100 people and measuring sort of them after treatment, and then running between groups for comparison. That'd be a stupid way to go about it, right? Because you're hugely wasting this resources and things like that. We just take the same people and measure them across two occasions. More efficient use of resources, and what we can do, and this is the huge thing, it allows us to control for and account for individual differences, random error. Everybody's serving as their own controls in these repeated measures designs, okay? Same individual measured on two occasions of context, less variable than two individuals measured separately, right? We only have one source of error if we're looking at sort of mean of the difference scores, as opposed to error in sample A, error in sample B, ends up being a much, much more powerful issue. I can't be like, oh, forget that now you're going to do this other thing, right? Once you know it, you know it. You can't unknow it, and now we have some problems, right? So again, from like an experimental standpoint, right, I can't be like, oh, hey, do this, and then forget I told you that, but now, hey, this is the other thing, don't think about that, right? Or if we're doing treatment studies, I can't say, all right, I don't want you to do CBT, and now forget CBT and take this sham pill, right? So these are carryover effects, things that we sometimes will preclude us from using repeated measures designs. We have additional assumptions with our repeated measures analyses, right? They start to become more complicated. There's more things we have to go through and take into consideration, and they start to get a little bit complex, right? There's just a lot of moving parts with these repeated measures designs that don't mean we shouldn't use them. It's just, if we're going to use them, we need to start thinking about things in a more specific way. Okay. Paired sample T. Again, remember what we're doing here is we're using our paired sample T to look at change in scores within individuals across repeated measurements, right? Our core outcome, right? Our primary outcome that we're using with our paired sample T test is our difference scores. This is our primary unit of analyses. Okay? So we're going to go through, we're going to say, here's scores at time 1, here's scores at time 2. Does SPSS care about time 1 and time 2 scores? No. Only to the extent that it uses those to create a difference score, and then what we're doing is we're saying, is the population mean difference score 0, right? Is the mean of the difference score in the population reliably different than 0? If it is, then we fail to, or we have evidence, if that difference score that we're getting, that's our observed difference score, exceeds what we would expect just due to random variation, we'd say, okay, we're going to reject the null, but if it's not, we're going to say, it's not exactly 0, but it's close enough. It's within the bounds of what we would expect just due to random variability and random differences. Okay? So, do difference scores across multiple assessments deviate sufficiently from 0 to conclude non and 0 difference in the population? That's functionally what we're doing. Remember, with our paired sample t-test, what we're essentially doing here is just a one sample t-test on the difference score, right? My hypothesis is the difference score, the value of the difference score is 0. And so this actually simplifies our formula quite a bit. We're looking at the mean of the difference score minus our expected under the null over the standard error of the mean of the difference. Standard error of our difference scores is going to be the standard deviation of the difference scores with the square root of n, right? And so again, this basically reduces down to a single sample t-test, right? if we've got example here, person A, B, C, D, right, time 1, 2, or time 1, time 2, calculate our difference scores. Mean of the difference scores is 3.5. Standard deviation of the difference scores is 3.87. This is what we're plugging in to our independent sample t-test to go through and test this stuff. Okay. And so again, our question here, what's the probability of obtaining a set of difference scores with mean difference of 3.5, assuming that null is true? Okay. All right. Questions on sort of that quick fly through and sort of getting us up to speed on stuff where we're at. Okay, cool. So we'll start jump into our repeated measures ANOVA next time. We'll run through some examples, some screening, actual work with some data,